All right, well, I'll get started. Today, talking about polynomial graphing and factoring again. All right, so in particular, though, I'm going to share with you a couple of theorems which are, well, I would say they're not obvious. I don't know if I would have, I mean, one of these theorems for sure I wouldn't have thought of. The other one, if you do more algebra, you might discover this one. But this is called the rational Roots Theorem, or in your text, it calls it rational zero theorem. And so what this theorem tells you is if you're given a polynomial, all right, then you can make a list of the possible values in the rational numbers. What's a rational number? It's a fraction, right? It's one integer over another, right? That's rational numbers. So this theorem will tell us what the possible rational roots are of a polynomial, right? Now, and so that's useful because it gives you a place to check, things to try. So let's let f be a polynomial. And I'll write it like this: f of x equal to an x to the n plus dot 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 plus a2x squared plus a1x plus a sub 0, where the leading coefficient an and the constant coefficient a sub 0 are both non-zero. And all the coefficients, a0, a1, all the way out through an, are elements of the integers. Right? So remember the integers, this is what? Like 0, plus or minus 1, plus or minus 2, et cetera, et cetera, et cetera. Right? Whole numbers and their negatives, also 0. Then, if f of p divided by q is equal to 0, all right, it must be that p is a factor of a sub 0 and q is factor of an. This is the rational roots theorem. So we put it into words. What we can do is we can look for possible ratios formed by factors of the constant coefficient divided by factors of the leading coefficient, right? So that gives us basically a method. So we can search for zeros of f of x by looking at factors of a sub 0 divided by factors of a sub n. That's basically the takeaway message here, right? Not just that, but if the polynomial has rational roots, then they have to be in here. Does every polynomial have rational roots? Can we give an example with one that doesn't have rational roots before we get carried away with this theorem? Let me just give you a caution. Not universally applicable. So for example, if we look at x squared minus 2, right? This polynomial we can factor, all right? So how would you do it? The difference of squares, right? This is x squared minus the square root of 2 squared. So we can factor that into x minus root 2 times x plus root 2, right? So this polynomial does not have a rational zero. What are the zeros of this f of x? It has roots of plus the square root of 2 and minus the square root of 2. The root plus the square root of 2 corresponds to what? The x minus root 2 factor. And the other one, x minus root 2, corresponds to x plus root 2. Right? Remember, there's this correspondence. The factor. What did the factor theorem tell us last time? You guys remember? What was the factor theorem? I mean, factor theorem is even more important, like way more important than rational roots theorem. We need to know factor theorem. That's got to be like hardwired in your thinking. What's the factor theorem? Nobody gonna tell me? All right, let me write it out again. Theorem. Factor theorem. It says f of c is equal to 0 if and only if x minus c is factor of f of x. In other words, there's a one-to-one correspondence between the zeros of the polynomial, the numbers which we can stick into it and make it output a 0, right? And the factors that correspond, like x minus c. So plus or minus root 2 is a 0 of this f of x, right? If I plug in plus or minus root 2, I get 0, because square root of 2 squared is 2. 2 minus 2 is 0, right? And also, we have this factor and that factor. Right? Okay, so here is an example of the rational roots theorem. And I called this example 1 in my notes, which I will, these notes I'm reading from right now, I'll post the PDF of this in course content for you, all right? But anyway, here's the example I come up with. F of x equal to 6x squared plus 7x minus 5, all right? So I just want to use this as a sort of a springboard for understanding the rational roots theorem. And so here we have a sub 0 equal to minus 5, right? And we have a sub 2, which is the leading coefficient, equal to 6, right? So what are the factors? Basically 1, 5. Factors here are what? 1, 6. Also? Yeah, 2 and 3, right? And they're negatives. All right, so, I mean, I should really say plus or minus 1, plus or minus 5, plus or minus 2, plus or minus 6, and so forth, right? So the rational roots theorem says we can look for rational zeros by looking at factors of a sub 0 divided by factors of an, right? So what does that look like here? What are the possibilities? What's the one thing you got? Don't forget about this one, 1 over 1, right? Because 1 is a factor of both, right? So 1 over 1 is a possibility. And of course, really plus or minus 1, right? Because we all do negatives. And let's see here, what else is a factor of a sub 0? Okay, so we can, let's just stick with the factor, let's stick with the numerator factor of plus or minus 1, right? And we can either divide by what? By 1, by 6, by 2, or by 3. These are all possible rational zeros, right? But there's more. What else can we do? we can use 5 from a sub 0, right? So also plus or minus 5 over 1, right? Which we just usually would write as what? Just plus or minus 5, right? And then plus or minus 5 over 6, plus or minus 5 over 2, plus or minus 5 over 3. And I bet, if you look at my notes, I bet I missed one of these at least. Yeah, check it out. So if I look at my notes, I've got 1, 2, 3, 4, 5, 6, 7 cases. How many cases are there? 4, 5, 6, 7. I got 8 up here. Or you could argue 16, right? Because plus or minus, there's 2 cases in each one of those. You know. So that means that for this polynomial, you've got 16 contenders, 16 possibilities that could be the rational roots, right? And again, none of them have to work, right? They could be. It's like this one, and there just is no rational root even defined. But I made this example up, and I can tell you they're rational roots. And so what do we do then? How do you figure out which one is the root? What do? You use the factor theorem, right? You just try plugging it in and see which one's 0. So where are you going to start? 1, I like 1. How about f of 1 is what? 6 plus 7 minus 5, otherwise known as what? 8, right? Is that 0? 8 is not 0. I think we can all agree. How about f of minus 1? 6 minus 7 minus 5. Well, that's no help either. That's 6. Minus 6, rather, which is not equal to 0, right? You want to plug in 5? Sure, why not? So f of 5 is 6 times 25 plus 7 times 5 minus 5, which is like 150 minus 35, 115, 110, right? That's also no good. Oh, negative 5? I don't think that one's going to go any better, but I'll do it. It'd be close. 6 times 25 again, minus 35, minus 5. So this time we got, I think I maybe did that last one wrong. I think that was supposed to be plus 35. I'm an idiot. This one is 110. What was the last one? Because I had 150 plus 35, which 150 plus 35 is 185, right? 185 minus 5 is 180, actually. Sorry about that. Anyway, it's still not 0. Man, you guys somebody's got to get lucky here. I'm telling you, at least one of these is a 0. You want to pick one, Heaven? 1/2? All right, I'll take a half. Let's try a half. F of 1/2, what do we get? 6 over 4, right? See what I did there? Why am I starting with 6 over 4? What's 1/2 squared? 1/4, right? So 6x squared is 6 over 4. And then plus 7 over 2 minus 5. I'm plugging in a half into the formula. What's that work out to? I recommend converting it all to quarters, right? So this is 6 plus 14 minus 20 all over 4, right? Hey, 20 minus 20 is what? That's 0, right? Is there a bug? It's just a what? It's a what? It better not be a hornet. Class is canceled. This is a hornet. I don't get paid enough. I got stung by a hornet in the face once, and it's no good at all. What's that? What? What? Oh, you're just now. I see you're That is very abstract. She says if we get to leave class with a hornet, then she's going to redefine all bugs to be hornets. That's the kind of nonsense a math major does. No, I feel like I've offended her, suggesting. All right, so 1/2 is a 0. So if we plug in 1/2 into this, we get 0, right? What does that mean? That means that x minus 1/2 is a factor of f of x, right? So this means we can factor out x minus 1/2, right? Now, here's my advice to you. In a problem like this, don't try to factor out x minus 1/2. Multiply this by 2. If you can factor out x minus 1/2, you can just as well factor out twice this, right? And factoring out twice this would be much easier to think about. So 2x minus 1 should also factor out. All right, so can you see that then? We have f of x equal to 2x minus, well, excuse me, it's equal to what? It's equal to 6x squared plus 7x minus 5. And I'm suggesting we can write that as 2x minus 1 times something. And what is that something? If we got a 2x in the first factor, what do we have to have in the other one in order to get 6x squared? Like, how can you get 6x squared? What we have to put here is what? 3x, right? We have to put a 3x there. We're forced to do that once we put that 2x there. And so what has to go over here? A 1 or a 5? Does it I guess my question would be, this is a 5, right? Oh, my 5s look like snakes, but anyway. What's that? Like an X? Oh, an S. Yes. I will agree. Here, I'll do better. There, proper 5. Now, so how do I get a minus 1 here? I have to put what? I got to put plus 5 here, right? And then we can check our work, right? So I have minus 3x plus 10x gives me 7x. Minus 1 times 5 gives me minus 5. 2x times 3x gives me 6x squared. We got it. Here we go. That is a factorization of that quadratic, right? You could have just done it, right? Right. Yeah, I think that's fair. Well, what I'm trying to do at the moment is to illustrate the rational roots theorem. Now, let me point out here, f of x, we can factor out a 6, right? And we can write x minus 1/2 and x minus what? If I factor out a 3 out of this, I get plus 5/3, right? So if you factor the 6 out front, you can rewrite the formula like that, right? Oh, you can use synthetic division if you like, but how would you know what to divide by? Oh, you mean just to divide the 2x minus 1 out? Yeah, sure. That wouldn't be bad. I'll do that with long division just a second here. But so what is the other 0? So we have f of 1/2 is 0. F of what else is 1, 0? So I said f of 1/2 is 0. We figured that out. And what's the other 0? F of what is equal to 0? Not 5/3, but negative 5/3, right? Is that in our list? It is, right? So here's the point of this example is to show you, hey, the rational roots theorem actually does work, and also, it's not a very good tool for this problem, right? Because there are way better ways to do this. One is just by, like you said, just write it down, just like guess and check, right? We could do that. What's another way we could factor this without using rational roots theorem? You could complete the square, right? Yes. But I wouldn't expect you to do that here really, though, because you'd have to do what? A lot of work. Well, completing the square here is kind of ugly because in this case, I'd have to factor the 6 out. Like that, right? And then completing the square looks like this. Divided by 2, that's 12. And then I have to subtract 49 over 144. And then how many times 6 is 144? 24? 24 times 6 is 144, is that right? That feels right. So what's 24 times 5? Well, 24 times 5 is 120. So I have to convert that to 144ths, which gives me, oh, that's kind of nice. So that's actually 6x plus 7 over 12 squared minus 169 over 144, which is pretty cool because that's 13 squared over 12 squared. So what you got is you got 6 times x plus 7 twelfths minus 13 over 12 times x plus 7 twelfths plus 13 over 12. I actually think, I mean, admittedly, the fractions here are kind of onerous. You know, they're not terribly friendly. The arithmetic here is a little tedious. But again, completing the square gives us like a straightforward, I mean, completing the square is a method which doesn't require guessing. It just requires careful arithmetic. And when you work this out, what is that? What's 20 twelfths? What's 20 over 12? Does that reduce? That's 5/3, right? Well, this one's 5/3. This one, what's 7 minus 13 is what? 7 minus 13 is 6. What's 6 over 12? Yeah, and it was the 13 wins, so it's minus a half. So yeah, I mean, same answer, right? Different, very, very different approach of finding it. Now, Stephen, you were asking me if we could instead use division to find the factor rather than like just guessing and checking, and absolutely we could also do that. I'll do it right here. You know, in response to Stephen's questions, yeah, we could have just divided. So what I'm explaining at the moment, guys, is this step right here. We could have replaced that with division, either synthetic or long division. So if I put 2x minus 1 here, you know, then I'm forced to put 3x, which gives me 6x squared minus 3x. You subtract, you get 10x minus 5. So that forces you to put plus 5, which of course is exactly what we found in the other way. So I mean, you're right. We could do it that way also. Listen, I want to leave the lion's share of class time for a different topic. So I'm going to use the projector here for a minute to show you my next example for rational roots theorem. It is much more beastly. And like this, okay, fine, right? We could use completing the square. We could just factor it. You know, you don't really need the rational roots theorem. I don't think the rational roots theorem really helps you at all, honestly. But I think it's useful as a starting point because it's, well, it's kind of familiar ground, right? The next example is trickier. So I guess I should probably turn on that projector if I can find you guys see the remote? It's hiding from me in plain sight. It's on the other side over there. Ah. So the theme of what we're doing right now is I'm trying to share with you a couple theorems which give us additional insight as to what are the possible zeros of a polynomial. All right. After the dust settles here, we're going to pretty much go back to what I did in the last class, and what I say at the end of this class as being sort of the more important part. So this is a little bit of a digression. I'm not saying it's not part of the course. I'm just saying that there are other more important things, but I'm not trying to give you license to ignore it. I'm just trying to give you a sense of importance. Okay, so if I can. And I'm sure there will be, I'm very bad at listing cases for things. Like I told you, I missed one in the notes already. So I'll try to pick up on those things as we look through this together. Let me go grab my laser. That thing is loud, isn't it? That bug, whatever it is. I think it's back up in like the window in the back. All right, so again, I'm going to post this for you guys, so don't feel the need to like write down everything here because you won't be able to. So this is the example we just went through, all right? And again, I'm missing what? Plus or minus 5 in this list. So I tried plugging in a third and a minus a third. Those are non-zero. And then I tried a half, and I was like, woohoo! So we found that. I found half first as well. And then once you find one, you can stop checking, right? Once you find one, then you can factor that out, and it should narrow your search. If it's a quadratic, once you've found one, that's kind of all you need, right? Because once you find one factor, it forces the other one to be whatever it is, practically. All right. Now this next example here, this one's a little bit tougher. All right. 42x to the fourth minus 83x cubed plus 53x squared minus 13x plus 1, right? So what are the possible rational zeros? Well, notice that here the constant coefficient's 1, right? And the leading coefficient's 42. Well, 42's got a lot of factors, right? It's got 42 times 1, it's got 3, it's got a 2, it's got a 7. So you can do 6 times 7 or 21 times 2 or 3 times 14. Lots of choices, right? So when we look at the possible rational zeros, a plus or minus 1, right? And then plus or minus 1 over 2, 1 over 3, 1 over 7, 1 over 14, 1 over 21, 1 over 42. These are all the possible rational zeros, all right? And again, we're going to use the factor theorem for guidance. We're going to look, are any of these 0? If they're 0, then we know there's a factor. So I start with the easiest one, which is 1. And this time, it paid off. F of 1 actually is 42 minus 83. Hey, stop that. Plus 53 minus 13 plus 1, which works out to 0. So that means we can factor out x minus 1 from this polynomial. And I chose to use long division. If you know synthetic division, you're free to do that. I have a long-standing blood feud against synthetic division. I can't teach it. I'm sorry. But long division will solve all your problems, so there you go. And so when we do the long division, what do we get? 42. Bring that down, subtract, right? 83 minus a minus 42 is really plus 42, right? So that gives me 41 minus 41, which then causes me to put this minus 41 up here. times x squared in order to produce the x cubed, right? And so forth and so on. And if we did things right, we should get a remainder of 0, right? By that remainder theorem we talked about before. And so indeed, this is what factors out. That's the cofactor of x minus 1, 42x cubed minus 41x squared plus 12x minus 1. And so great. We've replaced the problem with factoring a quartic to now factoring, we still got to factor this, right? This will factor, all right? The question is how? Well, if you think about it, that also has to share the same possible rational zeros. So, I mean, logically, F2 of one of this list, if it's going to have another rational zero, one of these guys should make F2 0 again, all right? So I can try any of those in F2, which I've defined right here. And if I plug in a half, what do I get? I plugged in a half, and I got 0. Okay, so x minus 1/2 is a factor of F2. All right? And so rather than doing that, I'll look at 2x minus 1, because that helps me avoid fractions. And so I factored 2x minus 1 by doing the long division, kind of like Stephen was suggesting for my easier example. And there it goes, right? The remainder is 0, so this is what factors out. Yay. All right, great. Now we're down to a quadratic, because I broke F2 into pieces. How do we factor the quadratic? Well, I suggest once we get to a quadratic, we shouldn't use rational roots theorem. We should just use plain old factoring, because it's just way faster to think through it. And this one, I looked at it and I was like, wait a minute. That's just 3x minus 1 times 7x minus 1, right? Because if you multiply that out, you get yourself the 21x squared, and you got a minus 7 and a minus 3, which gives you minus 10, you know. And 1 times 1 is 1, of course. And so there we go. We have factored this rather ugly thing with the help of the rational roots theorem into, x minus 1 times 2x minus 1 times 3x minus 1 times 7x minus 1, right? And then if you wanted to put this back into sort of like the standard form, we could like divide, we'll factor out a 2 and a 3 and a 7 from the last 3 factors, and when I do that, I get a 42 out front. And so there you go. This is the completely factored form of the example above, right? So, yeah. So this is a pretty hard problem, right? If I gave this to a class of 20 students, I think the odds of anybody getting this is about 1 in 20. And this is an in-class test. It's pretty tough, right? There are a lot of steps to get to that, isn't there? A lot of steps. But we could check our work at the end of it all, right? Because if this is right, it should be a relatively simple matter to go back to the start and check. Is f of 1/2 0? Is f of 1/3 0? Is f of 1/7 0? We already checked f of 1 being 0, right? So if you go back and you can check that those things are 0, then it stands to reason that this is probably correct, right? The 42, well, this 42 multiplies that x by that x by that x by that x, right? So there had better be a 42x to the 4th in the original formula. Was there? I think there was. And so that's like another double check on our math. See, we started with 42x to the 4th. So after you factor things, you can think about the process of multiplying it out and sort of double check yourself on the numbers and things like that. So it's not, there's some things in math where you do like 2 pages of arithmetic stuff, and at the end of it you're left with something that you can't really check. It's like pieces or structure. This is not like that. There's like a lot of things we could do to look at to see whether or not we made a mistake in the middle, Anyway, I'll shut up about that. Let's see here. So what's, this is, conceivably this could be a test question, right? But what is a better way for me to test the rational roots theorem that wouldn't force me to hope that you got through 2 pages of gory arithmetic correctly. I could just do what? I could say, here's a polynomial. What are the possible rational zeros, right? And so the question isn't do all this. The question is to give me the list at the start, right? Like the question, an easy way to test the rational roots theorem is not to ask people to actually use it to factor something. It's just to provide this list, right? Or I could make my life even easier, and I could say, provide for me the possible positive rational zeros, and then I wouldn't have to take points off for people not putting plus minus, you know? Then people told me, well, 1, a half, a third, a seventh, a 14th, a 1/21st, and a 1/42nd, you know, that would be the answer. That's often how you see people test the rational roots theorem, you know? Okay. Anyway, let's move on. Here is another example. X cubed minus 2x squared minus 9x plus 18. So the rational roots says the possible rational roots are formed by factors of 18 divided by factors of 1. What are factors of 1? Plus or minus 1, okay? So that's it. And what are factors of 18? Well, 1, 18, 9, 2, 3, and 6, I think. So that's why I have possible zeros of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus, what is that? I feel like it's a 6, and that better be a 6. Plus or minus 9, plus or minus 18. And so this is a much nicer, like this is much more, this to me feels like a more appropriate test question than like the last example. I just wanted to show you how it could help you with a truly hideous problem. This one is kind of more friendlier question. I think this is more appropriate for like a test, right? Because it's not like so many fractions and, you know. That's right. That's the weird thing. The rational roots theorem is so weird in that sense, right? It only depends. Isn't that striking? What are the possible rational zeros? Just depends on the leading coefficient being 1 and the constant coefficient, in this case being 18. It doesn't matter what happened in between. I mean, it does in the mechanics of which one actually becomes the zero. But as far as the rational roots theorem is concerned, you just look at those two numbers, which is kind of shocking, right? It's really weird. Anyway, so when I plug in those numbers, 1 minus 1, 2 worked out to 0, and 3 worked out to 0, and minus 3 worked out to 0. At that point, we're done. See, this is the thing. If you can find as many zeros as the order or the degree of your polynomial, then you're done. This is a cubic polynomial, right? So if I found 3 zeros, that means that there's an x minus 2 factor, there's an x minus 3 factor, there's an x plus 3 factor. That's all I can have for a third order polynomial, because when you multiply those back out, you get an x cubed, right? If I put another one, I'd have more than x cubed, then that wouldn't make sense. So once you've found 3 zeros for a cubic, you're done, right? So once I found these 3, then I can just put it together and check the leading coefficient. It makes sense, right? Since the leading coefficient is 1, I don't need like that 42 in the other example we looked at, right? There was a 42 in the other one because the leading term was 42x to the 4th. Like that 42 is not needed here because we have an x cubed in the original problem. So there it is. And you notice here, what did I not even need to do? Did I do any long division? I didn't need to do any long division. I really didn't need to do any factoring. All I did was make educated guesses about what the zeros were, and from that information, I can put together the polynomial. That is much easier than what we've done so far today. So I like, and there's at least one problem in the recommended homework which is like this. I'm trying to remember which one it was, but it says something like, I think it says, assume that the zeros are integers. I suspect it's very much based on this example. I'll shut up. All right. And of course, we could fall back on our previous devices and do long division to discover the cofactor and then factor, you know. So, but anyway. Next up, and I'll mention this ever so briefly. I don't really expect you to, this would not be on the test, all right? I might have a homework problem on it, but that's kind of as far as it's going to go. But I think it's worth mentioning. There's something else called Descartes' rule of signs, which is, it's a very interesting thing. So the way it goes is this. If you have a polynomial, you know, with coefficients a sub 0 through a sub n, and then the result is this. The number of positive real zeros of the polynomial equals the number of variations in the sign of the non-zero coefficients of f of x, or equals less that number by an even integer. And likewise, the number of negative real zeros of f equals the number of variations of the non-zero coefficients of f of minus x, or else equals that number less an even integer. To me, this is a very, like, what? I mean, it's hard to even understand what the theorem means. So this example helps explain. So this 3x squared minus 4x to the fourth plus 3x cubed plus 2x squared minus x minus 3. You go like plus, minus, plus, plus, minus, minus. So we've got like one sign variation here, another flip-flop of signs here, another flip-flop of signs here. Those three variations in sign. So what Descartes' rule of signs says is that there's either one or three real positive zeros for f of x. That's pretty neat, because if you were going to like look for where the, you know, if you were to look where to look for where f of x is equal to 0, and you needed your answer to be positive, this would tell you that you could either have one positive solution to f of x equal to 0, or you could have three positive solutions to f of x equal to 0. But you couldn't have just, you know, like, you couldn't have 4, for example. You can't have 2 either, right? You might be able to have 2 in the sense that you'd have 3, but one of them's repeated. I'm not sure about that. And then here's the f of minus x could also have, it has 3 variations of sign, so that means it's either 1 or 3 negative real zeros. But anyway, I just mentioned it in passing. Yeah, I mean, if I teach this course again, I won't cover Descartes' rule of signs. I just think it's too far in the weeds. It's not super helpful to what we're doing, and it's pretty hard to understand, I think. So this, on the other hand, is much easier. This we need to understand. This is the intermediate value theorem. And the intermediate value theorem is what it sounds like. It says that for a polynomial, if you go from x1 to x2, and like suppose x1 is to the left of x2 on the number line, then if n is a number which is between f of x1 and f of x2. Give it a second, it'll pass. I mean, this place is a ghost town. Like, the odds of people walking by in the hall and talking are pretty low, right? So, anyway, so this would be like if the function's increasing, so f of x1 is less than f of x2. On the other hand, this would be like if the function was decreasing, you know, so f of x2 is smaller than f of f1. Anyway, the point is, if n is a number between where the function starts and where the function ends, from x1 to x2, any number between those two values, there has to be some point in the middle where it cuts through it. This is because polynomials graphs are continuous, right? You can draw the graph of a polynomial like with your pen without lifting it, right? There's no jumps in the graph of a polynomial. So, I mean, here's a picture of it. If this is f of x1, this is f of x2, and n is a number between that in the y values, then there has to be at least one point between x1 and x2 such that f of c is equal to n, right? Now, where this is most useful for us is when we look at two different values of the polynomial, and one is negative and one is positive. What does that mean? In between where it's negative and where it's positive, there has to be a point in the middle where it's 0, right? So we can use this principle to do what's called root finding, right? And so this example isn't especially good. I'm going to skip over it. So here's the root finding algorithm. You know, suppose you want to see whether a polynomial f of x has a solution on some closed interval, what you do, you check the value of the polynomial at one endpoint, check the value of the polynomial at the other endpoint, right? And then check the value of the polynomial at the midpoint. If on either the left or the right-hand side there's a change in sign, if it goes from plus to minus on the left or the plus to minus on the right, then you're going to focus your attention on where that sign flip happens. And then you're going to go there and you're going to cut it in half again. You're going to bisect it again. And you're going to look at that like midpoint of that half section. And then you're going to look again for a place where the change is from plus to minus. And you're just going to keep subdividing the interval down and down and down, each time looking for where the sign changes in the polynomial. In this way, you can find zeros by bisection. Here's a numerical example. So f of x is 10x squared plus 8x minus 24. And I want to say, can we solve f of x equals to 0 on the closed interval from 0 to 2? So what I do is I calculate f of 0 and I calculate f of 2. Minus 24 and 32, guess what? It changes from negative to positive, right? So by the intermediate value theorem, yes, there has to be a 0 somewhere in there. Somewhere between 0 and 2, there is a point which makes f of c be 0. So I then look at the midpoint between 0 and 2, which is 1. I calculate f of 1. F of 1 is minus 6. So, okay, so I don't know for sure anything interesting happens between 0 and 1, but I do know something has to happen between 1 and 2. There has to be a 0 for the function somewhere between 1 and 2, because there's a sign flip from minus 6 to 32. And then I divide it again. The midpoint of 1 and 2 is 1.5. I calculate f of 1.5. I get 10.5. Okay, so if f of 1.5 is 10.5, there's nothing I can say for sure about between 2 and 1.5, but hey, between 1 and 1.5, I'm going from minus 6 to 10.5. So there's a sign flip. So I'm going to focus in here, and then I subdivide again. What's in between 1 and 1.5? Well, 1.25 is in the middle there, right? So I calculate what's f of 1.25. I get 1.625. So again, I'm going to focus between minus 6 and 1.25, because that's where between 1 and 1.25, that's where the sign flip is. And you just keep doing this, down and down and down. Each time subdividing and picking the next midpoint on the basis of where I get a sign flip. And so I do it. I can't picture it very well, but my x5 is 1.875, and that gives me f of 1.875 is minus 0.4. And then x6 is the midpoint of 1.25 and 1.875, which is 1.21875. I calculate that, I get f of that is 0.6. And then that suggests that I should look at the midpoint of the 1.875 and the 1.21875, which is about 1.203. I calculate f of 1.203, I get about 0.099. And that is very close to 0. And you could subdivide further. You can get closer and closer and closer and closer to where you're going across, right, changing from negative to positive. You've done this with your graphing calculator in high school, right? Haven't you done this? You look at the graph, you zoom in, and you zoom in, and you zoom in, and you zoom in, right? That's what this method is. It's nothing more than that. It's just doing it with a graphing calculator as opposed to doing it with a zoom function on the... You do the zoom function on the graphing calculator. I'm suggesting you could also do it just as well with pen and paper and a scientific calculator if you wanted to. It turns out actually that f of 1.2 is equal to 0, so we're getting pretty close here with just a half-page work. All I'm trying to tell you is the intermediate value theorem is a useful tool. It can guide us to come to some pretty quick conclusions. For example, can you factor a cubic polynomial? Why? And I don't mean in the sense of like I write down an arbitrary cubic. Well, let me write down an arbitrary cubic and ask you the question again. F of x equals to 13x cubed minus 30x squared plus 7. Can you factor that cubic? What's that? Yes? Okay, well, how do you do it? Well, oh, well, just because the rational roots theorem doesn't always work. If it worked, I would be very surprised. Although maybe it's useful to write down what is rational roots theorem. What is, I mean, fair enough. What are the rational roots theorem? What are rational roots possible here? So we need like a sub 0 factors over what? Over a sub 3 factors, right? So factors of what? Right. So I mean that pretty much means this is actually a better test question than my previous ones because there are not many answers here, right? So like 1 over 1, plus or minus 1 over 1, because 1 is a factor of both, right? Don't forget about that. Of course, we could have 7, plus or minus 7, plus or minus 13, and, well, plus or minus 7 over 13. I think that's it. Yeah, we're not allowed to do that. So you could calculate these 8 numbers, and if f of any of these numbers is 0, I would be like, I think the word is flabbergasted. Give you 20. Yes, if any one of these numbers works out to 0 with correct arithmetic on the given polynomial as currently stated, I will give you 20 points on the next test. You have it. It's on video. 13 minus 30 plus 7. We got what? Minus, I feel like this is a kind of a waste of class time, but it's also kind of fun. 24. Well, oh, I see your odds are now down to 7. 7 more possible choices. That's not 0. You're a gambler. Well, you know, that is actually literally true because I didn't really put any. Hey, wait a minute. What's in it for me? I forgot to ask. That's an important question. How about how about I get 10 extra minutes today? I'm just kidding. Anyway, that's not equal to 0. And you can work it out. If any of them 0, let me know. But so my point here is just that, no, I mean, this cubic would be pretty difficult, I think, to directly factor. It's not a special form like a cubed minus b cubed or a cubed plus b cubed kind of pattern. Like those we can do, right? If we could factor an x out or see like factoring by grouping, we can do those. But like just an arbitrary cubic, if I ask students to factor it, that's unfriendly. That's just a fundamentally unfriendly question. However, if I ask students the question, does a cubic have a factor? And I don't actually tell you to, to find it. If I just say, explain to me why it does, that's a very easy question. Because all you have to do is furnish me 2 numbers, right? One of which has the cubic being negative, and the other one, which when we evaluate the cubic at, we get positive. Well, then intermediate value theorem says it has to change from minus to plus. It has to be 0 somewhere in between, right? So can you give me an input which will make this negative? Yeah. You're working too hard. How about 1? What's f of 1 equal to? I'm not going to calculate f of 13. No. 13 minus what? Minus 30 plus 7, right? If you evaluate f of 1, you get that, right? What is that? Negative 10, right? And what's f of 0? No, f of 0. Look, the original. What's f of 0? Oh, that's a good question. I don't know. How on earth did I get 24 there? What? You guys got to ask me about these kind of things. I mean, it had something to do with me spending 2 days of this week doing nothing but lifting furniture and like junk like that. But oh yeah, I'd like to blame it on that. So yeah, 10 minus 10. Anyway, so the conclusion doesn't alter, but golly, how on earth did I get 24 there? I just don't even know. Anyway, f of 0 is what? I heard 7, right? If you plug in 0 to here and 0 to here, you should get 0 minus 0 plus 7 is 7. 7. So what does this mean? This means if you graph this polynomial, right? At 0, it's 7, right? And at 1, it's like minus 10, right? What does that mean? That means that it has to cross through 0 somewhere between 0 and 1, right? And so I'm not telling you where that happens, and I don't know what happens past here. Not exactly. Actually, I'm pretty sure I know what has to happen. I can tell you what has to happen. Here's some other thinking we can use. If x, the absolute value of x, is much, much greater than 0, then f of x, for all intents and purposes, is 13x cubed. What I'm trying to tell you is there's a principle of graphing polynomials. The leading term wins after a while. If you have x really, really large positive or really, really large negative number, that 30x squared and that 7 doesn't mean anything. Like you put in a million cubed is so much bigger than a million squared. Even put in 1,000. If you put in 1,000, this is like a 13 billion. This is a what? 30 million. What's 30 million to 13 billion? 13 billion, way bigger, right? So it doesn't take long for the leading term to dominate the expression. So if I want to think about, in my mind's eye, like what this graph looks like really far away from the origin, I just focus on the leading term. And so I know that this looks like 13x cubed if I'm really far away from it, so to speak. Which means that, roughly speaking, this thing looks like this. Right? Now, it is not exactly that, is it? Because it actually has got this behavior between 0 and 1, doesn't it? If you zoom in. But I know from this, what's going to happen is this has got to turn around and it's got to go up like that. And this guy's got to turn around and it's got to go down like that. I'm not sure where that happens exactly, but that's what it's got to look like. So this is why the intermediate value theorem is very useful, because it allows us to sort of see what's happening even when we can't like actually factor something out, right? Did I tell you where this actually is? No. It's somewhere between 0 and 1. Is it a half? Is it a quarter? I have no earthly idea, and it doesn't matter if we just want to graph. What's that? 0.033. So any of these work out? So sorry. I guess the moral of the story is you're going to have to study for the next test. Study.